So next we move on to one more type of PMF that you can have once you have random variables and events. This is called conditional distributions. Okay. So first we look at just one random variable. Okay. So it's a very simple case where if you supposing you have a random variable x that's defined in a probability space, and let's say there's an event that's defined A. Okay. One can define something called conditional PMF of x given A. Okay. So this is just a PMF which is Q of t, you can denote it Q of t, anything else if you want you can denote it. Basically it's the probability that x equals t given A. Okay. So previously the PMF of x without any conditioning is simply the probability that x equals t. Now if there is an event A with which you want to condition, then probability that x equals t given A becomes a conditional PMF conditioned on an occurrence of an event. Okay. So this makes sense, you can see why this makes sense. We will use this notation x given A for denoting the conditional random variable. You have an unconditioned random variable x. If you want to condition on event A, I will simply say x given A, x bar A, that is the conditional random variable, and that would have a distribution which is different from the original random variable. Okay. So how do you compute this fx given A of t? It's basically probability of x equals t given A. That's just probability of intersection of those two events divided by probability of A. Okay, so standard conditioning, nothing changes in the actual equation except that the conditioning has come in. Okay, so this is a general conditioning in terms of an event, but even here pay attention to the fact that the range of x given A can be different from range of x. Okay, because once you condition on A, x may not be able to take many values outside of A, right? So the range can change. Okay, so this conditioning makes sense. Sometimes it's used, people do condition on events, but it's most popular to condition on events defined by another random variable. Okay, and that's where the conditional distribution of one random variable given another random variable's value enters the picture. Okay, so it's sort of very similar to the previous picture, except that this event A is now defined using another random variable. Okay, so let's say you have two random variables x and y. These are jointly distributed. They have a joint PMF if x, y. The table is given to you. Okay, so remember the table is given to you. I'm going to define something called the conditional PMF of y given x equals t. Okay, so x equals t has occurred. The random variable x has taken a value t. So the event x equals t has occurred. Now, of course, I can define now the conditional random variable y, which is conditioned on x equals t. And that's exactly the conditional PMF of that guy. Okay, so basically it's the probability that y equals t prime given x equals t. Okay, so you can just do this calculation again. This is just an ordinary conditional probability now, right? Y equals t prime given x equals t. It's probability of y equals t prime comma x equals t. Remember, comma is and, right? So it's the intersection y equals t prime and x equals t divided by probability that x equals t. And notice now what is the numerator? Numerator is the joint PMF fxy of t comma t prime, and what's the denominator? Denominator is the marginal PMF fx of t. Okay. Now we'll use this little notation here. Hopefully this notation is clear enough. I will say y given x equals t is the conditional random variable. Okay, I'll think of that as the conditional random variable itself, y given x equals t. Okay. So what is this q of t prime? It's nothing but the distribution of this conditional random variable, right? So we'll write it as f y given x equals t of t prime. Okay, so it's a very common notation for the conditional random variable. Okay, so what's most important about the conditional random variable is this equation. Okay, so this equation is something that we will use quite a bit when we write down joint PMFs and all that. Okay, so the joint PMF, it's the same thing, it's the same equation that's used in the definition. I've written it a bit differently. Okay, so the joint PMF evaluated at t comma t prime, x equals t, y equals t prime, is simply the product of the conditional PMF of y given x equals t of t prime times fx of t. Okay, do you see that? It's the same equation, fx of t comes in. Okay, so this is the same product rule that we used when we defined probability of A and B, right? What's probability of A and B? It's probability of A given B times probability of B. It's the same thing, except it's written in the language of conditional PMFs and joint PMFs. That's it. Okay, so this equation is very useful. Quite often some of the objects here may be easier to find. Okay, so quite often it's very common that the marginal is easy to find and the conditional is easy to find. Okay, and then you can multiply the two to get the joint. Okay, or maybe the other way around, but usually the marginal and the conditional are easier slightly to define than the joint directly. Okay, so this is a very common trick that is used to get to the joint PMF. Okay, so hopefully the definition was clear. Now let's check our understanding with some examples. So here is a very simple example. Okay, so here is a joint PMF. Okay, so notice how the joint PMF and the marginal are given to us. Okay, so notice how what this joint PMF is. From the joint PMF you can identify that the range of x is 0, 1, 2. Okay, so better way to write range of x is this, I mean x belongs to 0, 1, 2, y belongs to 0, 1. Okay, and the joint PMF is given. You can quickly check that it's all valid. 1 by 8 appears 4 times, that's half. 1 by 4 appears twice, that's another half. It all adds up to 1, and you can do the marginal here. You just add up everything in the row, you get half. You add up everything here, you get 1 by 2. You get here 3 by 8, 1 by 4, 3 by 8. All of these are valid as well. Okay, so everything is fine. So now, supposing I want to do the PMF, let's say, for y given x equals 1, x equals 0. Let's take that. Okay, so y takes value 0, 1. I want to do y given x equals 0. Okay, so this random variable, it takes value 0, 1. Okay. And what is f y given x equals 0 of 0? Okay, it's f x y of 0, 0 divided by f x of 0. Okay, what is f x y of 0, 0? It's 1 by 4. And what's f x of 0? That's 3 by 8. So you get 2 by 3. Okay. What is f y given x equals 0 of 1? It's f x y of 0, 1 divided by f x of 0. It's basically 1 by 8, right? 0, 1 is 1 by 8 here. Okay. Divided by 3 by 8, you get 1 by 3. Okay. So notice what has happened here. To get the conditional PMF, you simply divide this column by this number. Okay. So you divide the column 1 by 4, 1 by 8 by 3 by 8 to get the conditional PMF 2 by 3, 1 by 3. Okay. So you divide 1 by 4, 1 by 8 by 3 by 8, you get that. So now if you want to look at the conditional PMF of y f x, let me go to x given y equals 1. Okay, y is 1, so you have to look at, and so if once y is 1, you look at, so maybe I should write it in another color. Let me pick another color for you. I'll pick this dark green. Okay, so this is y equals 1 for you, and this is the probability that y equals 1. You divide this by this, you're going to get the distribution here, right? So y equals x given this is going to be 0, 1, 2, and the probability is going to be, let me just do it in green, the probability is going to be 1 by 8 divided by 1 by 2, right? I'll write it like that, 1 by 8 divided by 1 by 2, and then 1 by 4 divided by 1 by 2, and that's just 1 by 4, 1 by 4, and 1 by 2. Okay, you don't have to write it in such great detail, you can just directly write if you like, 1 by 4, 1 by 4, 1 by 2, I got that. So this way you can quickly see how to find the conditional distribution. Any conditional distribution I give you, you identify the row or the column and simply take that, divide by the marginal that comes below it. That's it, that gives you the conditional PMF. Okay, very, very easy and straightforward way to find conditional PMF. Okay, so let's do one more example to convince ourselves that we have understood this. Here is the example I want to do. So here's a joint PMF that's been given to us. Okay, you can check that this is a valid PMF very quickly. You can just add 1 plus 3, 4, 7, 5, 12. Yeah, so this is a valid PMF. It adds up to 1. Okay, so here the marginals have not been given, and you have to just keep computing some of the conditionals. So let's look at this. So here first step is to compute the marginal, right? So if you add up these two, you get 4 by 12, which is 1 by 3. Here you get 3 by 12, which is 1 by 4. Here you get 5 by 12. Okay, so here again if you add, you get 1 by 2, 1 by 6, 1 by 3. Okay, so those are the marginals, that's okay. So now if I want to find y's, so the range of y, so remember x takes value 0, 1, 2 and y takes value 0, 1, 2. Okay. Now if I want to find x given y equals, or let me start with y given, okay, y given, let's say we do y given x equals 0, okay. So this guy, okay, so this is this divided by this guy, right. This is going to be 0, 1, 2 and the probability is going to be 1 by 6, 1 by 3 and 1 by 2, isn't it? Do you see that? Okay, so you take, see x is 0, so I know I have to focus on this column alone. If I take this vector in the joint PMF, divide by the marginal, I am going to get the distribution. So notice how y given x equals 1 is going to change. Okay, so if you say y given x equal to 1, you see there is a 0 there. The moment there is a 0 there, you don't want to include it in the range and put a probability 0. So you drop it. So you just say 1, 2, okay, 1 by 12 and 1 by 12, and probability is total is 1 by 6. Notice the total doesn't matter when these two are equal. I know ahead of time that this is going to be half, this is going to be half, right? Anyway, but you can also divide and check that that works out. Similarly, you can do y given x equals 2 and that's going to be, so notice the way I am writing it, I write the values taken below and the probability above. Okay, so this you can use any such simple notation. So given x is 2, maybe I should do a different color here. So let me just do a different color to be very clear on what's going on. So supposing you look at y given x equals 2. Okay, so I'm looking at this column and then I'm going to divide by this quantity here. That's going to be 0, 2. I don't have to write the 0 explicitly, right? Because that's going to take a probability 0 there. Why do that? Okay, so you'll get a 3 by 4 and a 1 by 4. Okay, so notice how you're getting different marginals, you know, I mean joint PMF for something and then depending on how the matrix is, you'll get different marginals. All of it is interesting. So let's also do a couple of cases row wise. So let me just do x given, I'll do a different color, maybe blue. Okay, so let's look at x given y equals 1. So y is 1, so you are focusing on this row here and this guy here. This is going to be 0 and 1. Okay, it doesn't take the value 2 because that's already 0. And then if you do 4, you're going to get 2 by 3, 1 by 3. Okay, so notice all the different probabilities that you're getting between all sorts of distributions 1, 2, 0, 2, 0, 1, 2 by 3, 1 by 3, 3 by 4, 1 by 4, half, half. All of these end up happening once you go to the conditionals. Okay, and in every case you can check the equality. Okay, remember to check this equality. It's always true that fxy of t1, t2 equals f, maybe I should start from the left side and right. This is an important little equality for you to know. fxy of t1, t2 is always equal to fy given x equals t1 of t2 times fx of t1, and it's also equal to f x given y equals t2 of t1 times fy of t2. So this is always satisfied. Okay, so you should remember this identity is very important. You can check in all our calculations. You can check that that holds. I mean, this is how we just calculate it. It's sort of trivial in some sense, but it's important to note. All these identities will be very, very useful. So somebody gives you a table, some partial information about conditional PMFs is given, this is given, some conditional PMFs are given, some marginals are given, some actual joint PMFs are given. You should be able to calculate all the missing values using these identities. Okay. One more thing I want to point out, which I think maybe was not very, very clear. So notice here the y given x equals 0 is actually sort of a random variable and it has a PMF. So if you keep x fixed and vary the values of y, right, you will get 1. Okay, so if you add up all these guys, you will get 1. 1 by 6 plus 1 by 3 plus 1 by 2 is 1. 1 by 2 plus 1 by 2 is 1. 3 by 4 plus 3 1 by 4 is 1, right? So every conditional random variable is actually a full-blown random variable. So it's a valid PMF. So if you do this, right, if you take sum over f y given x equals t of t prime and add it over all y, okay, you will get 1. Okay, so this is also an important identity to remember. Okay, so the conditional PMF is a valid PMF on its own. So you add up over all the range. In fact, it may not be the entire range. It may be something smaller than y also. But anyway, let's add it over the entire range. Maybe some of the values will be 0. It doesn't matter. You add up the conditional PMF over the entire range of y, you will get 1. So this property is also very important when you solve problems. Okay, so the conditional PMF is a valid PMF on its own. It will take probabilities and you add up all the probabilities, you will get 0. You will get 1. Sorry, add up all the probabilities, you will get 1. Remember, x equals t is fixed here. Okay, so you can't keep changing x. Okay, so x equal to t has to be fixed. It has to be one conditional random variable. Then it's PMF. When you vary y alone, y given x. When you keep x fixed and vary y, and you look at y given x, that will give you 1. Okay, so that's an important identity to remember. Okay, so I think I've covered most of the things. You can check all these things. It's useful to know. Okay, so I have a few examples to show you. Maybe this is a good point in the lecture to break and then come back and see the next lecture. Thank you very much.